So we're gonna, so this is sort of in one dimension. I'm gonna come back a little bit later to talk about, in fact, we probably will do this in the next class to talk about 2 and 3 dimensions. But I wanna talk about kind of a special property of Laplace's equation. And that has to do with the idea that, you know, I solved this differential equation, right? We had a simple equation, we got a straight line, right? Now, if I had a different set of boundary conditions, I would get a different solution. So different boundary conditions give different solutions. Right? So if I said, you know, at x equals 0, it's 10, I obviously would have gotten a completely different answer here that I would have boxed. I would have got a different answer. But what would be a good, what we're not clear on, what's not obvious is, can I get 2 different solutions with the same set of boundary conditions? And the answer is no. That's the short answer. And the reason for that is has to do with this sort of special property, this special idea called the uniqueness theorem. And the uniqueness theorem says that as long as the potential V is specified, on the boundary, there will always be only one solution, right? So as long as I have a set of boundary conditions, this uniqueness theorem is saying there's no way I could come up with something other than this answer that I got here, right? And so let's prove that. Let's prove that by sort of assuming I have 2 different solutions, and then we're going to show that those have to be the same. So let's prove that and say, let's just sort of assume we got 2 solutions to the Laplace equation that both satisfy the boundary conditions. Right? Because if it didn't satisfy the boundary conditions, then it's not helpful, right? So let's assume we got 2 solutions that satisfy the boundary conditions, and let's just say that's V1 and V2. So we have like a V1 of X and a V2 of X, and both of them fit in with the differential equation. Like I take their second derivative, I get 0, and they both satisfy whatever kind of boundary conditions we have. We don't really care what they are at the point. So what that means is these two solutions, if I do del squared V1, I'm going to get 0. And if I do del squared V2, I'm also going to get 0, right? So they both satisfy Laplace equation. And so what I want to do is I want to look at the difference. I want to look at the difference, and I'm going to call that V3, which is just equal to V2 minus V1. So this is a new function, V3, that's V2 minus V1. And so since V1 and V2 satisfied the same boundary conditions, then we know that V3, we know that V3 satisfies the same boundary conditions. Ugh, not used to writing on here. So just by default, since V1 works and V2 works, we know at least on the ends that V3 has to do the same thing, right? Again, the good way to think about that would be like V1 at x equals 0 is, let's say, 2. Well, then I also know for sure that V2 at x equals 0 also has to be 2. And so therefore, V3 at x equals 0 is going to satisfy the same boundary condition. Right? I'm going to subtract them and I'm going to get 0. So that these values are always going to be the same. Okay, so let's just try it out. Now let's see, does this new thing that we started with, V3, does this satisfy Laplace's equation? Let's try it out. If I do del squared V3, I'm really just doing del squared V2 minus V1. And so not surprisingly, I can distribute this, right? If I take a derivative, I can just distribute the derivatives. And so I can do del squared V2 minus del squared, minus del squared V1, right? And so from above here, I already know that del squared V2 and del squared V1, I already know that both of those are 0. Right? So I get 0 minus 0, that equals 0, right? And so what that's telling me is that V3 satisfies Laplace's equation. And because it satisfies Laplace's equation, because V3 satisfies, because it satisfies Laplace's equation, V3 must be 0 everywhere. So it's not just 0 on the boundaries, like we have because of the boundary conditions, it's 0 everywhere. And if it's 0 everywhere, then that means V3, which is equal to V2 minus V1, is 0. So V1 is equal to V2. So these are the same solutions. Right? And so what we've just proved here is that if I can come up with one solution, that's the only solution. I don't need to guess and figure out if there's going to be some other answer somewhere. So as long as I can find one solution that fits the boundary conditions, then that is the only solution. So I don't need to kind of guess around and look for anything else, right? And that's really important because what we're going to do is we're going to take advantage of that and say, I'm going to come up with a really complicated problem. A problem that we wouldn't really normally be able to do with just our simple integration that we started with here. And if I can't do it with that, what I can do is just swap out a difficult problem swap out a difficult problem for an easier one with the same boundary conditions. Because all that matters is that the boundary conditions are the same.